right, so let's get started. Okay, so this section of topics is basically kind of like a review or a broader topic section about particle size measurement. So until now, we showed that we talked quite a lot about particle sizes, right? So we basically mentioned that sizes are important because it affects how the performance of the different control methods are, right? So for example, if we use some, if the particles are large enough, right, it can just settle down by gravity and we don't even need to care about that. And if the particles are very small, then they will have a higher penetration through a lot of the control devices. So that's why the particle size is very important. But until now, the only instrument that we talked about that measures the particle size is what? It's the impactor. Right? It's a cascade impactor. So I think at the end of last class, I think Clayton asked a question. So if some of you stayed a little bit longer. So Clayton asked a question about what is the difference between the impactor and some other measurement techniques? So although we can directly say that impactor, but it's quite straightforward, right? We collect the particles on different stages, and then we measure the mass. We know what is the concentration at different size range. But one important disadvantage is that the impactors, they don't differentiate a lot of sizes, right? It's just a few, maximum 10 stages. We don't have a lot of size bins there. And also it covers larger size range, typically above 1 microns. But right now, people know that the particles that are most toxic are actually below 1 micron. So those can stay in the air for longer time, and those can penetrate through our respiratory system more easily. So that's going to pose a higher health threat to the human. So that's why we have to invent or explore a lot of particle size measurement techniques. Okay, so this class we're going to review, or we're going to introduce a few currently being used particle size measurement instruments. Okay, so first we can briefly introduce about the sources of the particles that we're interested in. So I remember in the introduction class of the PM, we mentioned about when we talk about the source, there are primary sources, there are secondary sources, or there basically it's either bottom up or top down, right? So bottom up are processes that is similar to reaction. Basically from combustion, we generate a lot of molecules, and then those molecules will combine together, right? And then form stable clusters of molecules. And then we also have the top-down method, which is basically some machine working, right? We're crossing the rocks, right? We're doing woodwork, right? Generating those particles. Those are top-down methods. So, but in reality, actually, there are many different types of sources of particles. Although we can categorize them into bottom-up or top-down approaches. For example, over the ocean, so actually there's no human made particles, right? So over the ocean, most of the particles are actually coming from the bubble bursting. So what happens is when we have the wave, right, the wave can generate those small bubbles, and when they burst, they're going to generate those tiny droplets. And those droplets can suspend over the ocean, and then they can get evaporated and form smaller particles. And actually over the ocean, a lot of the clouds, we mentioned that the cloud droplet is actually at the center of it has to be a particle, right? A lot of those particles are coming from the bubble bursting over the ocean. So basically the particles can be composed of sea salt or organics, right? Also the ocean also generates a lot of gases, different types of gases. And forest fires, I know these days, this is a quite important topic, right? We know that the wildfire over the West Coast is very severe right now. So it generates a lot of particles and it impacts the human health, visibility, and also the local climate. Later you will see basically those particles, once they get emitted into the atmosphere, they can form different types of clouds, right? And, basically affect the radiation. So there are primary biological aerosol particles. So these can also come from forests. So you can think of them as the like tiny microbes. Okay, so tiny microbes, some of them generate spores. Right, those spores are suspended particles, so they can generate particles, and also a lot of bacteria can generate particles. And actually, these microorganisms themselves, while they disassemble, they can basically burst into tiny particles. So one interesting study that people did in the Amazon forest is that we know over the forest, the relative humidity changed quite a lot. So overnight, the RH can go as high as 100%, right? And during the daytime, the RH can be quite lower. So what happens is, because of the high RH, these bacteria can absorb a lot of water, and basically they burst out. So once they burst, they generate tiny fragments, basically form a lot of particles over in the forest. Okay, so there are also dust, right? This is a picture showing basically from the desert, you generate a lot of particles there. Volcanic ash. This is also a very important natural source of the particles, mainly because whenever it happens, it just emits large quantities of PM. So there was a report about a volcanic eruption in Europe. So basically, the statistics tell people that from that eruption, the global average temperature actually dropped by 0.5 Celsius, mainly because these particles get suspended in the air, they form clouds, they block the sunshine, and then cause some radiation problems. So basically, the temperature dropped down. So we mentioned secondary organic aerosols. So these are basically the secondary processes that's forming the aerosols over the Smoky Mountain, right? We talk about Smoky Mountains, not because of people do campfires there. It's because of those reactions in the forest. So there can be urban aerosols or urban smog. These are just, for example, fossil fuel combustion, coal-fired power plants, or diesel engines, car engines, and so on. And finally, it's a combustion aerosol. Again, it's similar to the urban smog here. So there are all different types of sources of aerosols, sources of particles in our daily life. So again, about atmospheric aerosols, they can range from a few nanometers to several microns. So we basically introduce a combustion, generate a lot of soot. So these soot can be a few, let's say this scale bar is 100 nanometer, I think. So each of these tiny particles can be very small, okay? And as the particle becomes larger, let's say pollen, it's going to be in the range of several microns. It's going to be larger sizes, okay? And also, because of their different sources, their chemical composition will also be quite different. So we mentioned that how PM is affecting our daily life, right? It can affect the radiation from direct light scattering or cloud fraction, cloud formation, right? So direct light scattering, one application is the radiation, the picture that I showed for the western coast, right? You have those orange or red colored sky. It's not because of the fire color, it's because of the radiation, right? So they can generate different sources, things, and they can evolve, right? And it can impact our human health and affect all different types of nano-engineered products. But actually, if you measure the particle size in the atmosphere, they look a little bit different from what we thought. So basically, if you push out an instrument, let's say that can measure particle size from, let's say, 1 nanometer to 100 microns, we know that the impactor can basically cover from 1 micron to 100, right? So it's typically in this range. If we also have an instrument that measures smaller size particles, we're going to see different modes. So for each of the mode, people actually name them with different names. So for example, if the particles are below 0.1 microns, which is 100 nanometer, so those particles are called the Aitken mode. Okay, so this is called the Aitken mode. And if they're below 10 nanometer, which is 0.01 microns, those are called the nucleation mode. Some people also call them ultrafine particles. And particles that are above 0.1 micron, which is 100 nanometer, this mode is called accumulation mode. So the reason why they call accumulation mode is mainly because when people measure the size, this mode is always there. It seems that they're accumulating in the atmosphere. And this has something to do with their removal, because this size of the particles, they're most difficult to remove. So similar to the masks, okay, so when we evaluate the filtration efficiency of the masks, these particles are very, very difficult to get filtered out, mainly because of the removal mechanisms, or they're leaving out particles within this size range. And further above 1 microns, people call that as coarse mode, or the sedimentation mode, right? So these particles can easily settle down into the onto the ground. So if we just consider about what are the typical particles that will exist in the air, I would say Aitken mode, accumulation mode will always be there. Okay, so coarse mode, it really depends on what are the sources. If it's dust, right, from the desert, they can exist in the air. The nucleation mode is also associated with the sources. Let's say if we're measuring the size that's close to a engine exhaust, then we can see a lot of small particles, which are in the nucleation mode. But most of the scenarios, we're going to see Aitken accumulation mode, okay? So yeah, again, so we mentioned that impactors can cover things that are above 1 microns, but what about below 1 micron? So we need instruments to do that, okay? So the concept that people use to basically to design these instruments is based on the electricity. So it's using something called electrical mobility, okay? So we always know that if we give some charges to an oil drop, we learn from the physics book, right? So if we have certain charges on an oil drop, and if we place it in an electric field, then we can somehow get it levitated. And that's because of the electrostatic force, right? So we can use the same concept to measure the particle size, okay? So let's say that we have two parallel plates, okay? So these two parallel plates are made of metal, right? So at the same time, we're introducing a very clean flow here through the two parallel plates. Let's just consider them as these two parallel plates, right? And then each of them has certain lengths and certain widths, right? So it's not a very large scale instrument. Let's say it's just the size of the palm. And we can introduce very clean air going through the gap between these two plates. So what happens is that basically this clean air doesn't have any particles in there, right? It's going to establish a velocity field, okay? So at the same time, let's introduce particles here. Let's see, okay? So let's introduce particles that we're interested in, okay? Introduce them. So now we know that because of the drag force, the particles will just move with the flow, right? Because there's a relative velocity, there's going to be a drag force. The drag force is going to pull the particles towards this direction, okay? So because we're interested in particles that are below 1 micron, so they're settling velocity, basically the terminal velocity that we learned in our last class, the terminal velocity will be very low. Remember that graph, right? So if the particles are below 1 micron, it's going to take maybe years or hundreds of years for them to settle down. So what we do is we actually give charges to these particles. Let's say we give them 1+ charge, okay? And then under this situation, let's say we put a negative voltage onto the bottom plate. So what's going to happen is there's going to be an electrostatic force, right? The force is going to pull the particle in this way. mainly because of the traction, right? And so what this means is that the particles will also have a force that's going, basically the vertical direction. And we know that once there's vertical movement, now it also has a relative velocity against this flow field here. So there's going to be a drag force that's pulling the particle upwards, right? There's going to be a balance. The particle tries to move down, so the drag force tries to pull it up. So there can be a balance of the force, and the particles basically will move with not a straight line here, not directly horizontal or vertical, but towards this diagonal type of direction. And now if we consider, basically, if we have very large particles, let's say if we have again, we use maybe not potato, because potato, the gravity is too large. Let's say we consider 1 micron particles. So for the 1 micron particles, if they are introduced into the field, they're going to go this way, right? But the electrostatic force that's on the particle is too minimal. It's not going to pull the particles towards this direction by a lot. So what happens is that larger particles, they will move along this line here, this top line here, okay? And for very small particles, because the electrostatic force is so strong in terms of its own property there, so this very small particles can quickly get pulled towards this vertical direction. So very small particles will flow along this line here. So now, let's say we cut an opening on the bottom plate, okay? So we know that only particles with a specific size can go through the outlet. So we call this as a classifier. Basically, we're classifying particles with different sizes, right? So if we introduce a bunch of particles with different sizes, larger particles are going to follow this direction, smaller particles follow this direction, and only particles with the correct size can exit from the outlet, okay? So now, basically with this instrument, people call this as the electrostatic classifier. So with this instrument, we can classify particles of a specific size, right? And now, if we want to measure, let's say, we want to measure the particle size distribution. We know particle size distribution, on one hand is particle size, on the other hand is concentration. So now we can measure size because it's classified by size. But what about concentration? Right? We need to also know what is the concentration of the particles. So basically, this is another instrument. This is the parallel plate electrostatic classifier, right? So basically, this one measures further smaller particles. These are ions. So if you introduce ions of different sizes, they're going to get separated into different trajectories. And only particles with the correct size can get classified, and then it can go to a different detector, okay? So again, so this horizontal flow, this clean flow here is the key, because they give the particles a horizontal velocity. While then on the vertical direction, you have the electrostatic force to pull the particle apart. So in this way, you can classify particles of different sizes. So in reality, of course, people can build these horizontal, these parallel plates, right? But in reality, people actually find out an easier way to deal with this. So instead of using parallel plates, they just use 2 cylinders, because cylinders are easier to manufacture, right? So if you go to the machine shop, you have the machine to make these very smooth surfaces. It's not like a flat surface, right? So flat surface, it's difficult to make sure that the surface is smooth. But for these cylinders, you can control the surface property very well. So what happens is that people make 2 cylinders. So you have a center rod and you have an outer rod. And it's using the same concept. So what we're doing is we introduce a clean sheath flow. This is the clean air that we talked about earlier here, okay? So these clean air are going to introduce a vertical velocity to all the particles that enter this instrument, okay? And at the same time, the particles will enter from the side of the outer cylinder. So basically, these two cylinders forms a gap, right? So theoretically, they're still parallel, right? Because the two cylinders, they're concentric, right? Theoretically, they're still parallel, but it's not a plate shape anymore. So basically, the particles are introduced from the side of the cylinder, and then similar to what we introduced in the parallel plate, larger particles are going to just go through this longer, more tilted diagonal line there, right? Smaller particles can get attracted very rapidly. So they will deposit here. And then at the end of the inner cylinder, we dig out a outlet. So basically, it's the same. So particles of a specific size can follow this central trajectory. So they can get classified by this two concentric cylinders. So basically, with this, we can classify particles of different sizes. So what people call this instrument is called a differential mobility analyzer. So it sounds quite complicated. So basically, it's just a classifier, okay? So it separates particles according to their size. And so as we mentioned, we want to measure particles of different sizes. So right now, let's say we give it a voltage of 1000 volt, okay? So we're separating particles of a specific size. So what about other sizes? This can only separate one size, right? So for other sizes, what we do is we'll apply different voltages on that. It's as simple as that, right? So let's say at the beginning, we set it as 1000 volt. And then later we change it to 5000. We change it to 5000, basically that will increase the electrostatic force on the particle. And that's going to be able to pull these larger particles to the outlet here, right? So we mentioned that the larger particles, because the electrostatic force is so minimal to them, right? So that's why they're not, their trajectory is not affected. But if we increase the voltage on the inner electrode, we're able to pull these particles further inward, right? And then we can classify those particles. And in terms of the particle size that's in between, what we can do is we can just scan the voltage, right? We were saying 1000 volts, 5000 volts, but why don't we just scan the voltage? 1000, 1100, 1200, all the way up to 5000. So in that case, we can basically classify particles of all different sizes, right? And this will generate particles of a specific size that we want. And now what we need to do is just measure the concentration, because we know the particle size, what the particle size is, and then if we know the concentration, we know what is the size distribution, right? So actually this concept has led to a lot of designs for the instruments. And right now the most widely used instruments that in the aerosol field is called there's a company that's called TSI. So they make these, basically these DMA columns, right? So you have the lone DMA, and we also have the nano DMA. So different types of DMA, they have the same working principle. It's just the size of the particle that we're interested in is different. For example, the lone DMA measure particles from 10 nanometer to let's say 600 nanometer, while the nano DMA measure particles from 3 nanometer to, let's say, 30 nanometers. Nano DMA measure for the smaller particles. Okay. So we mentioned that basically with this device, we can classify particles of specific sizes. And then how do we measure the concentration, right? So actually, our school is has some history with this instrument. Right? So the major principle that people measure the concentration is by using the condensation. Okay, so you may have the experience. Right now it's still quite early, but during the winter, whenever we exhale air, we can see white fog in front of us, right? So that white fog is because of condensation, mainly because the exhaled air has a lot of water vapor with it, right? And when it also in the ambient environment, there are a lot of particles. And then if it's exhaled, because of lower temperature, these water vapor are going to condense onto the particles. And then basically grow them larger. And that's why we see those fog particles, okay? So condensation is is not a very complicated process. So basically, whenever we have lower temperature, we're going to see condensation. So during the winter time, or maybe late fall, you can see these frost or fog on your windshield. That's because of the condensation, right? So now by using, how do we use this concept? So basically, the thing is, we can use water vapor or use all different types of vapors to grow the particles. And once it's grown, we can see them with our bare eyes, right? So of course, when we really count the particle number concentrations, we're not going to count it one by one. Nowadays we can just use lasers or use cameras. And those machines, they can auto detect whether there's a particle or not. But in terms of the basic concept, it's always the same. So here I have a short video about why this condensation concept can be used in the detection of particles. Okay. Yeah, so this is the experiment that's done in Antarctica. Antarctica is one of the most cleanest area on the Earth. So typically the concentration is below 10 particles per cc. So remember earlier in the class we introduced the typical concentration particles indoors. The typical concentration indoors are thousands of particles, right? But in Antarctica, the concentration particles is very low. So can you guys hear the audio from this video here? I mean, if you can you just type in the chat? If you can't, I have to adjust something, okay? No? Let me see. Okay, now it should be good. Let me start from the beginning.
Okay.
What about now?
There's no particles.
Just breathe, right?
Yeah, just breathe. So there's the particle concentration is 5 per cubic centimeter.
You ready?
Yep. Let's see. No breath. Turn on the other side so the sun faces you. So yep. No breath. Minus how much? -8. You can't see it because there's no particles, no fog. Nothing.
Right. So it's quite different from here where we're staying in, right? Because there's no particles, condensation won't be able to form the fog droplets, so we can't see that.
Yeah. So Kathy, would you just demonstrate that this is hot tea?
How do I demonstrate with this?
Because you put it inside, and if you start diluting and changing color, that means it's hot. So there's no flow.
So we have some hot tea here.
Hot tea here.
I'm about to stick some Earl Grey into this cup of hot water.
And there's
hardly any steam coming out.
Because there's no particles.
Want to walk inside? Want to walk inside and show how much steam is coming out?
Sorry?
You want to go inside and show how much steam is coming out inside?
Yeah.
This water is really hot. Okay, so we're going to walk inside. So you can see what it looks like. How much steam's actually coming out with really clean air.
Oh, I don't have a lighter. Do you have a lighter?
Yes, I do.
Oh, just put the lighter. Just come, Kathy.
Oh, okay.
Just put the lighter above the steam.
Instead of going inside, we're just going to put a lighter over it. Look at that.
Oh my God.
Look at that.
Particles?
Particles? No particles.
No particles.
Why is this?
Particles?
Because lighters produce huge amounts of very small particles.
Yeah, all right.
Yeah.
So the pollution from the lighter.
Pollution from the lighter causes the fog to be formed.
Great.
And just to prove that we are at the...
Can I drink this so I don't freeze?
So to thank the demonstrators.
Yeah, we'll just.
That's
Cheers.
Nice
Yeah.
experiment.
All right. So basically, what it's showing is that the steam that we see and also the fog, exhaled air, the fog we see, it's because of particles, right? So basically, we can use this concept to measure particles. So once we can see them with our bare eyes, we can also see them with all different type of detectors, lasers or cameras. Okay. So actually, our school played a major role in inventing this instrument. So this is a figure that's showing a design of an instrument that's called the condensation particle counter. So condensation particle counter basically counts how many particles there are by using the condensation. Okay. So this is a schematic diagram of the instrument. I think this is published in 1970s. And you see, it's made in University of Missouri, Rolla. Okay. I think it belongs to the chemistry department. So next time when you go there, I think most of their old instruments are in the basement right now. So last time when I go there, I see quite a lot of familiar instruments with, which are looks very old, but you can tell what they're being used for. So if you're interested, next time you go there, you go to the basement, take a look. Okay. So basically, this is an instrument that uses condensation to count how many particles there are. It's using water to condense the particle, to basically grow the particles. So this is a chamber, right? So you can basically move the, there's a piston here. So you can expand the volume or squeeze the volume of this chamber. So because of the change of the vapor pressure, you're going to emit more water vapor in the environment in this chamber here. So these extra water vapor can condense onto the existing particles. And you can see basically the fog droplets. And each of the fog droplet represents one particle. So basically you can later on, I think at that time people are still using bare eyes or using cameras to take a picture and then count how many particles there are. But nowadays we can use some faster measurements to count, so basically measure what is the particle number concentration. Okay. Okay, so it seems that this is the last slide, right? We can come back to this instrument here. So what we can do right now is we can couple this particle condensation particle counter to measure what is the number concentration of the particles that's being classified, right? So what happens is, let's say we apply 1000 volts of the high voltage onto this base plate here. And then that's going to drag out, that's going to classify particles of, let's say, several hundred of nanometers. And then they can, after they are classified, they can be introduced into this condensation particle counter. So we can measure what is the number of the particles with this size, right? And then if we further scan the voltage that's applied onto this base plate, we can basically obtain the particle number concentration as a function of size. So that will give you the size distribution of particles. So this instrument is widely being used to measure particles, size distribution of particles below 1 micron. Because if you consider what are the major difference between this one and the impactor, right? The impactor uses inertia, right? So particles have to be heavy or have to be large enough to get collected onto the stage, right? And then you can measure the mass. But this one, you just need to scan the voltage. You just need to scan the power that's applied onto the electrode, and then you can get a wide size range of particles. So they're using different forces, right? One is just using inertia, the other is using electrostatic force. And also, if you consider what are the advantages and disadvantages, so the advantage for the DMA or for this method is that you can do continuous measurement. So each scan, they can just for, let's say, 1 minute. You scan for 1 minute, you get a size distribution. And then for a day, you can get so many measurements. But in general, for the impactor, you have to collect for a very long time so that you can accumulate enough mass and then measure or then let you know what is the mass concentration, right? Because after particles are collected on different stages, you have to go to a scale and then to tell you what is the mass. And in general, those scales that we have cannot differentiate very small mass. So which means that we have to accumulate for a long time. So for example, right now the EPA, when they use the impactor to measure the particle mass, they will just set up the impactor there for a whole day. So basically during the entire day, it's expected that we can get enough mass to let us know what is the mass distribution or the size distribution. But during the whole day, a lot of things can happen, right? It might be very clean in the morning and in the evening, but very polluted at noontime. So basically, the impactor, the cascade impactor, can't give you enough time resolution, while these instruments can give you real-time measurements, right? So it can give you the size distributions after each minute, right? So you can get a lot more information regarding the dynamics, right? So let's say we want to measure the air quality nearby an industrial plant. Let's say the industrial plant only emit these pollutants during noontime, okay? They just emit for 5 minutes. So if we use a impactor to measure the the size distribution, we won't be able to tell when they're being emitted. But with these instruments, which have higher time resolution, we can basically obtain more information from these measurements, okay? Let's see. I would say that's all for the contents of this class. Again, I apologize that the technical issue is happening. Actually, I already uploaded slides for this class onto Canvas. So we'll continue with that in our next class. Okay, so next class we won't have this problem. So if you want to stay for longer, you can also let me know your comments, right? So until now, what do you think of the class? If you want, you can unmute yourself. Everything's good? If you want to type in the chat. Okay, so, yeah, good. So have you guys started the project? At least look at the emission or calculate the mass of the coal for the power plant. So I would say for this project, since we learned quite many related concepts in the beginning, it's better that you start to practice with these calculations, right? And because you have more team members, now you can have a cross check, okay, make sure that the answers are correct. And so yeah, so I think at the end, when you make the presentation, all the other teams are going to compare the results with yours, right? So if there's one number that doesn't make any sense, want to quickly identify that so you don't show those errors inside. Okay, so I hope the homework problems are okay. Also, by the way, I think I received a few emails about the homework clarifications. So I think for this homework 3, it involves the calculation of the mean free path. Okay, so in the class I didn't write the equation for the mean free path. So basically you have to refer to the textbook to calculate what that is, because at different temperature and pressure and for different gas molecules, the mean free path will be different. So I introduced that under normal condition, let's say 25 Celsius, 1 atmosphere, the mean free path of air molecules is 68 nanometer. But the mean free path for other different temperatures is going to be different, okay? So you want to refer to that equation to calculate what is the actual mean free path, and then compare with the particle size. So, so also related to this point, so remember in the class, we also talked when the particle size is much larger than the mean free path, we have the Cunningham correction factor close to 1. So some of you ask me, what does it mean by much larger? So we typically just use larger, the sign symbol for the larger, and then double that to show that it's much larger. But in terms of mathematics, I would say if it's 100 times larger, that's much larger. If it's 1% or lower, that's much smaller. So you can use this as a guideline to calculate what is the basically what is a Cunningham correction factor. Because if the particle is too large, let's say 1 micron, that is much larger than if it's 10 micron, then it's much larger than the mean free path. So we don't need to worry about Cunningham correction factor. We can just regard that as 1, right? So again, I want to emphasize that there are 2 major takeaways from the class. One is a definition of particles. I really want you to memorize that. One is the equation for the drag force. The drag force is 3 pi mu dp divided by c, okay? So next time we'll have a quiz on this equation. So try to memorize this equation. It's going to be very convenient for a lot of the calculations we use in the class, all right? So any other questions? Good. All right, so if no more questions, we'll just stop here. So next class, we're going to continue with the single particle dynamics, okay?